In this video, we're going to be looking at 5 different basic trigonometric identities. Now, these 5 identities can be a lot to try to keep track of, so as a result, on any quiz or test that you'll take for this class, I will provide 4 out of the 5 for you. The only one that I will not be providing for you is this first one. And what these trigonometric identities allow us to do is it helps us find the values of other angles. If we're just given, like for example, if I'm given the sine of one angle as 0.1625, I can use that fact in these trigonometric identities to find other angles that have the same sine value, or even to be able to find the cosine value. And so you're going to see how these identities all work together. But like I said, you only have to memorize and make sure you know this first one, but the other 4, you need to know how to use them and how to apply them. But I will give you the list of those 4 on the quiz and on the test. So let's go ahead and take a look now at these 5 identities and look at some application for them.
Okay, so again, this first identity is called the Pythagorean Identity Theorem, which says for every angle theta, the cosine squared of theta plus the sine squared of theta is always going to equal 1. And if you notice, this is very similar to the Pythagorean theorem, a squared plus b squared equals c squared. The reason why this is equal to 1 is if you recall from our unit circle, the radius of our unit circle is going to be 1. And when we use this Pythagorean identity, we're working with triangles, right triangles, where the hypotenuse would be the value for c. So basically this is just saying that again, that the cosine squared of theta plus the sine squared of theta is equal to 1 is based on the Pythagorean theorem. So let's see how we would use this. So this first example says to find the cosine of theta when it equals 3/5. So all we're going to do is we're going to take 3/5 and square it because we know that value of cosine. So it's going to be the 3/5 squared plus the sine squared of theta will equal 1. So what we're going to do is we're going to square each side. So we're going to square the 3/5, both the numerator and the denominator, giving us 9/25. And now I just have to get the sine squared of theta by itself by subtracting 9/25 from both sides. But you got to be careful, because when I subtract 9/25 from both sides, we got to look at this 1 as having a common denominator. The 1, I'm going to change this to be 25 over 25. So now when I subtract 9/25 from it, we can do that. Because remember, you can't work with fractions unless they have common denominators. So now I would have sine squared of theta equals 25 minus 9 is 16 over 25. So now to find out what sine is equal to, we're going to take the square root of both sides. But you got to be careful. Remember, when we take the square root of both sides, we're going to end up with 2 solutions, a positive and a negative value. So in other words, the sine of theta here is going to equal the square root of 16 over 25 is going to be 4/5, but it's going to be plus or minus 4/5. Now for this one, we don't know whether it's positive or negative, so we just leave it as plus or minus 4/5. Now if the angle that we were looking at was in the first quadrant, well, the sine of anything, or the cosine of anything in the first quadrant for that matter, would be positive. So if we were doing the same problem and we knew that the angle was in quadrant 1, we would only care about the positive solution. Now if we were working in quadrant 3, where the y values would be negative, then we wouldn't worry about the positive solution. We would only be concerned about the negative solution. So when you know the angle measurement, it's important that you take a second and check to see which quadrant it is to figure out which solution we're going to use. We're going to skip example 1b. We're just going to go to the next identity, which is the opposites theorem. And the way this one works is it's saying that the rotations of magnitude theta and negative theta go in opposite directions. So here's what they're saying. If I have a rotation of 100 degrees, that would bring it over in quadrant 2. A rotation of negative 100 degrees would bring it over this direction. If you notice, the values here, where this red p is and where p prime would be opposites of each other for the y, but they would be the same value for the x, because they have the same x value here, but they have opposite y values, because they're a reflection over the x-axis. So that's what it's saying here, that they're going to have the same first coordinates, so the cosines are going to be the same between those 2 points, and the y values, the signs are going to be opposites. So the opposites theorem basically says a cosine of the opposite of an angle is the same as a cosine of an angle, or the sine of the opposite of an angle is going to be equal to the opposite of the sine of the angle, and the tangent of the opposite of an angle is going to equal the opposite tangent of the angle. So that is your opposites theorem. The next one that we're going to look at is called the half-turn theorem. The reason why it's called a half-turn is because we're rotating our angle 180 degrees. Because if you think about it, if we add 180 degrees to any angle, it's going to flip and be the opposite quadrant. For example, if I had my unit circle here, if you think about quadrant 1, where x and y are both positive, if I were to rotate that 180 degrees, it's going to be down here in quadrant 2, where they're both going to be opposites. Or if I had a number in quadrant 2 where x is negative and y is positive, if I rotate that 180 degrees, it's going to be, both are going to be opposites. The x would now be positive, the y would now be negative. So anytime we take an angle and add 180 degrees to it, it's going to be the opposite. So here's how we describe that with the cosine. The cosine of 180 degrees plus an angle would be the opposite, the cosine of the angle. The sine of 180 degrees plus an angle is going to be the opposite sine of the angle, and the tangent of 180 degrees plus an angle is going to equal the tangent of the angle. And it is also true for radian values. Remember that in radians, pi is equivalent to 180, so it would be the same thing, just using pi. So that's our halfway or half-turn theorem. And we're going to look at some examples here in a minute where you'll have to use or figure out which one of these theorems we'd use to figure out our solutions. Now remember, in geometry you've learned about supplements. A supplement is to an angle is where together the two angles would add up to be 180 degrees. Or another way to look at it is if we know a measure of an angle, its supplement has a measure of 180 minus the angle measurement. Or pi minus the angle measurement, or in radians if we're working in radians there. So the supplements theorem, the way that we use that for sine is that the sine of 180 degrees minus the angle is equal to the sine of the angle, or the cosine of 180 degrees minus an angle is equal to the opposite cosine of the angle, and the tangent of 180 minus an angle is equal to the opposite of the tangent of the angle. Again, we have these also in radians using pi in place of 180. So let's look at this example so you can see how we would use the supplements theorem. So here we're given the angle of 10 degrees is 0.1736. So the sine of 10 degrees, I should say, is 0.1736. We want to find a value of x other than 10 degrees between 0 and 360, for which a sine of x also equals 0.1736. Well, we can use the supplements theorem for that to find another angle. So to use that, we would say, use a different color here. We would say that the sine of 180 minus 10 is equal to, using our supplements theorem here, we're going to say it's equal to the sine of the angle, so it's equal to the sine of 10 degrees. So in other words, 180 minus 10 is 170. So sine of 170 degrees equals a sine of 10 degrees, so that means the sine of 170 degrees is also equal to 0.1736. So that's how you can find another angle that has the same sine value. Now we have another theorem. Remember back in geometry we also learned about complements. So the complement of an angle is where we have two angles that add up to be 90 degrees. Or another way to look at it, if we know the measure of an angle, its complement is going to be 90 minus the measure of the known angle. Or if we're working in radians, now if pi represents 180 degrees, pi divided by 2 would represent 90 degrees in radians. So in place of 90, we would work with pi over 2. So in other words, looking at this box for this complements theorem, the sine of 90 degrees minus an angle is equivalent to the cosine of an angle. And the cosine of 90 degrees minus an angle equals the sine of an angle. Again, if we're working in radians, we replace 90 with pi over 2. Now, we just got finished talking about these 5 different identities. Let's look to see how we would use these now for some different situations. So let's look at this first one here. So the first one is asking us, well, we know that the sine of 30 degrees is 1/2. So we want to use that information to figure out what the cosine of 60 degrees would be. Now, this is the first time we've done some of these, so I'm going to have to walk you through these, but the more you practice them, the more you're going to be able to see which one would be the best theorem to use. So for this one, for cosine of 60 degrees, what I recognize is that 60 degrees is the same. I could use the complements theorem. Because the cosine of 60 is the same as the sine, using the complements theorem, of 90 minus theta. And by the way, if you have my notes online, what I've done for you is this last page, I printed all of these theorems out in one spot, so you don't have to flip around for them. So it would be a good idea if you have access to my notes to print those out, or at least that last page, so you can have all of those to look at all in one place. So now going back to this one, using the complements theorem, we would say the cosine of 60 is equivalent to the sine of 90 minus theta. Or, I guess it'd be better to say 90 minus 60. And the reason why I recognize that is because 90 minus 60 gives me the sine of 30. So that's the only way that I could figure out what the cosine of 60 is. So the cosine of 60 then is equal to the sine of 30. So that means that, well, if the sine of 30 is 1/2, that means the cosine of 60 is also equal to 1/2. Okay, again, we got that by using the complements theorem. Let's look at B. For B, this is a cosine of 30 degrees. Now, here's a hint. Anytime they give us the sine of an angle, and we know the angle measurement, and they ask us to find the other trigonometric ratio, so in this case here, they're asking us to find the cosine of the same angle, the hint is that you're going to always use the Pythagorean identity theorem. So I'll just abbreviate that as a Pythagorean identity theorem here. So in this case here, it's going to be the cosine squared of 30, which, oops, is what we're trying to figure out. Plus the sine squared of 30, well, we know that the sine of 30 is 1/2, so this is going to be plus 1/2 being squared. Together, that's going to equal 1. Now, I know that 1/2, when I square that, is 1/4. And I know that 1, when I end up subtracting 4 from both sides, 1 is the same as 4/4. So when I subtract 1/4 from that, I get the cosine squared of 30 equals 3/4. And now to figure out what the cosine of 30 is, I would take the square root of both sides. So when I do that, I'd end up with the cosine of 30 equals, now technically you would say plus or minus the square root of 3/4. But a couple things about that. For one, the cosine of 30 is in quadrant 1, so we're not going to worry about the positive, or I'm sorry, we're not going to worry about the negative square root. All we care about is a positive. And I don't want to leave this as a square root of 3/4, so I'm going to take the square root of what I can. I can't take the square root of 3, but I can take the square root of 4. That's going to be 2. So my answer here is going to be the square root of 3 over 2, and it's a positive value. So the cosine of 30 degrees is the square root of 3 over 2. And we use the Pythagorean identity theorem to give us that answer. Okay, let's look at sine of 150 degrees. Now this one is more than 90 degrees, so I'm not going to use the complements theorem. It's closer to 180 degrees though, so I can use the supplements theorem. So the supplements theorem would say that the sine of 180 minus 30 would be equal to the sine of 150. And the supplements theorem says the sine of 180 minus theta is equal to the sine of theta, which in this case would be the sine of 30. So that means that the sine of 180 minus 30 is 150. So the sine of 150, which is what I'm trying to find, is equal to the sine of 30, which is 1/2. So sine of 150 degrees is 1/2. Now let's look at the cosine of 210 degrees. For this one, it's more than 180, so I can't use the supplements theorem, and I therefore can't use the complements theorem. It's not the same value as what I was working with originally, so I can't use the Pythagorean identity theorem, so I've narrowed it down. It can't be any of those three. it's not, I can't use the opposite theorem, so that leaves me with the half-turn theorem. So the half-turn theorem tells us that if we have the cosine of 180 plus theta, in this case it would be 180 plus 30, would give me cosine of 210. That's equivalent to the opposite cosine of theta. In this case, theta would be 30 degrees. So in other words, the cosine of 210 degrees equals the opposite cosine of 30. Well, we found cosine of 30 in part B to be square root of 3 over 2. So this is going to be the opposite of that. So it would be negative square root of 3 over 2 would be our answer. And lastly, we have not used the opposites theorem yet. This is the one this is where we're going to use the opposites theorem. So this is saying the sine of negative 30 degrees. Using the opposite theorem, we would say then that the sine of negative 30 degrees equals the 30 degrees. So that means the sine of negative 30 degrees, if the sine of 30 is 1/2, it's going to be the opposite of that, so it's going to be negative 1/2. Okay, let's try some more. These are going to be a little bit faster. Let's look at this one here. This is asking us for the sine of x equals 0.681. So here, I don't know what my angle measurement is, but I do know that they're asking me for the opposite value and the fact that it's going to be the same angle. So it's the sine of x and the cosine of x. So this tells me I'm going to use the Pythagorean Identity theorem. The Pythagorean Identity theorem tells us that we would have the cosine squared of the angle, which we don't know what that is, plus the sine squared of the angle, which we know that is 0.681, equals 1. So to figure out what the cosine would be, I would subtract 0.681 squared from both sides. And when we do that on our calculators, 1 minus 0.681 would end up being 0.536. Take the square root of both sides. And now, again, since I don't know the angle measurement, it's in general terms, I need to remember that I'm going to have two solutions. The square root of 0.536 ends up being 0.732, but it'll be plus or minus 0.732. Would be my answer. Now to find the tangent of x, remember, is found by taking from the previous lesson the sine of x divided by the cosine of x. Well, they gave us the sine of x is 0.681, and there's two possible solutions for the cosine. It could be a plus or minus 0.732. So that means when I divide these out, I'm going to have two possible solutions for my answer. I could have a plus or minus, because 0.681 divided by a positive 0.732 is going to be 0.930. But then if we divide by a negative 0.732, it's going to be a negative 0.930. So our answer would be plus or minus 0.930. Let's look at the next one. The next one is asking us to take the sine of the opposite of x, so we can use the opposites theorem to say again that the sine of the negative x is going to be the opposite of the sine of x. Well, if the sine of x is 0.681, this is going to be negative 0.681. And this one is in radians. These last two are in radians. So this is saying the sine of pi minus x. Well, remember, pi is the same as 180. So here they're setting it up for us. It'd be the supplements theorem, 180 minus x, or pi minus x, equals the sine of x. Again, this is the supplements theorem. And so the sine of x we know is 0.681, so my answer would be 0.681. And lastly, again, this is in radians, and this is 180 plus x. Remember, if we're adding 180 degrees to something, we're dealing with the half turn. So we're going to deal with the half-turn theorem. And the cosine of pi plus x, according to that theorem, is going to be the opposite cosine of x. Well, we found what the cosine of x was back in step A. Step A, we found that it's going to be a plus or minus 0.732. Well, the opposite of that would also be plus or minus, because the opposite of a positive 0.732 would be a negative 0.732. And the opposite of a negative 0.732 would be a positive. So again, it's going to be plus or minus a positive 0.732 for that one. So there you have it. I know that seemed like a lot of information to cover, and it is, as far as knowing those 5 identities and knowing how and when to use them, but that's why we did so many examples here. It's important that you work these examples out in your assignments, and that way you can make sure that you understand them, because the only way you're going to learn how to use which particular identity and which particular theorem is if you practice it on your own. So I encourage you to make sure that you do that, and with that, good luck.